Okay, so let's finish up our discussion of section 4.5 by looking at harmonic motion. I'm not going to get into a ton of detail about this. I feel like this is a lot of these things are like physics topics, you know, that would be best taught by your physics instructor, but but we can at least get our feet wet a little bit with some of these kinds of things. Anyway, repetitive movement back and forth through an equilibrium or central position is called simple harmonic motion. And examples of this would be like a string with a weight attached to one end, right? If you pull it down and then let go, that's just going to oscillate back and forth, and it's going to pass through an equilibrium position 0. And I have a little link to a video here which you can watch on your own. It's just like a little animation of this idea, but the idea is that if you were to plot the distance of the weight from the equilibrium position as a function of time, then what you would get is a little sinusoidal curve, right? So so it makes sense that we would be talking about harmonic motion in conjunction with like graphs of trig functions, and in particular graphs of sine and cosine, the sine and cosine functions. Anyway, other examples of harmonic motion would be like a pendulum on a clock, or the vibration of strings, like on a guitar string, right? So all these things involve simple harmonic motion. So the position of a point oscillating about an equilibrium position at time t is modeled by one of these two functions, where the absolute value of a is the amplitude of the motion, and omega is the angular speed. Okay, so just like the angular speed that we talked about in chapter 3, at the end of chapter 3. Okay. The number of oscillations or cycles per unit of time is called the frequency. So the period can be thought of as how long it takes for one complete cycle to occur. So in this case, right, if you're multiplying t by omega, then the period would be 2 pi divided by omega, right? The frequency, on the other hand, is how many cycles occur within a particular unit of time. Thus, it's the reciprocal of the period. So the frequency is just the reciprocal of the period, right? In this case, omega over 2 pi. So in other words, period is cycles per second, while frequency is, period is seconds per cycle, while frequency is cycles per second. Okay? So period is how long it takes to complete one cycle. Frequency is how many cycles it completes in 1 second. All right. Anyway, but the math is not difficult to work out on these kinds of problems. So let's look at a couple examples. This is a really short section, by the way. But anyway, suppose that an object is attached to a string. It is pulled down a distance of 5 inches from its equilibrium position and then released. The time for one complete oscillation is 4 seconds. Oh, that's so slow. How could that even possibly be true? There's no way, right? What spring takes 4 seconds to complete one oscillation? Anyway, we'll go with it though. It says, give an equation that models the position of the object at time t. Okay. Alright. Well, first of all, we're told that the weight is pulled down a distance of 5 inches. So that 5 inches, that must be the amplitude. Right? The amplitude. Because if they pull down the weight 5 inches and then they let go, it's going to come back up to its equilibrium position, and then it's going to continue to go up 5 inches before it falls back down. And so you're going to get this this amplitude of 5 inches. Okay, and then the time for one complete oscillation is 4 seconds. So it takes 4 seconds to complete one complete oscillation. That's the period, right? That's the period. Okay, so when they say give an equation that models the position of the object at time t, we're going to use one of these two functions. We'll use the, since they pulled the spring down 5 inches and then they started counting time once they let go, it's like the spring was past its equilibrium position. So we're not going to use the sine function, because the sine function would start at time t equals 0 with the object at equilibrium. Cosine is going to start at 1, but we can multiply that by a -5 so that it's starting at -5 where it should, right? Anyway, so we'll use the cosine function, but we need to figure out what the amplitude and what the angular speed is. We know the amplitude's 5. The angular speed, though, we need to solve for, but that's easy because we know that the period is 4 seconds, right? So 4 seconds equals 2 pi over omega. Okay? Which means that omega is 2 pi over 4, or in other words, pi over 2. So the angular speed is pi over 2 radians per second. So we could say, you know, this is in radians per second, right? Anyway, but that's it. So then the position function s of t is going to be, we want it to start below equilibrium position 5 inches. So it's going to be -5 cosine of pi over 2 times t, and then that's all there is to it. Now in the real world, we know that eventually the spring is going to stop oscillating, right? It's going to oscillate, it's going to make shorter and shorter oscillations until eventually it just comes to a stop. But this is sort of like a theoretical thing, like if you removed friction and heat loss and all kinds of stuff like that. So if you had like this ideal situation, then this would be the function that models that behavior. Okay. Part B of the same problem says determine the position at time t equals 1.5 seconds. Well, this is easy now that we know that, by the way, s of t was -5 cosine of pi over 2t. So since we know that, finding the position is not difficult. We just plug in 1.5 for t. .5 is the same thing as 1.5, which is 3/2. I'm just saying that so it's a little easier to do the math. Because this would be now 3 pi over 4. And cosine of 3 pi over 4 should be the same thing as negative cosine of pi over 4. That's negative root 2. So this is -5 times negative root 2 over 2. So that would be 5 root 2 over 2 is the exact answer. For an approximation, 5 root 2 over 2 is about 3 point, we were given 2 sig figs, so we'll say it's about 3.5. What was this? Inches, right? 5 inches. So it's at about 3.5 inches. And since that value is positive, that tells you that it's above its equilibrium position. So it's about 3.5 inches above its equilibrium position. It's kind of cool. And then part C, find the frequency. Oh, I forget the symbol for frequency. Like the period, the symbol for the period is T, I believe. What's the symbol for the frequency? I'm not sure I gave it. So we'll just call it F. I think it is lowercase f. But anyway, the symbol for the frequency I think is F. And F, as we've said, is omega over 2 pi, right? So F is omega divided by 2 pi. Omega we decided was pi over 2. So this is pi over 2 times 1 over 2 pi. Pi's cancel. 1/4. So it makes 1/4 of an oscillation in 1 second. That makes sense, right? Because it takes 2 seconds, I think we said. No, it takes 4 seconds to do one complete oscillation. So in 1 second, it does 1/4 of an oscillation. So that makes perfect sense. Okay, so that's really all there is to this section. You'll be asked to work out problems like that. You might also be asked about things like this. So it says the voltage E in an electrical current is modeled by this function here, where T is measured in seconds. Part A asks us to find the amplitude and the period. So the amplitude is easy. That's just absolute value of this number right here. So the amplitude is 3.8. The period, which I'm going to call t, is, well, for the cosine function it's usually 2 pi, but it looks like we've multiplied this one by 40 pi. So it's going to be 2 pi divided by 40 pi. Pi's, of course, will cancel. You get 1/20th. Okay? Or if you like, that's 0.05, right? So 0.05 seconds, right? Seconds. So that's how long it takes. And I don't know what this is measured in. Well, it's voltage, so this must be volts. So it's 3.8 volts. And this is seconds, right? So it takes 0.05 seconds for one complete oscillation, one complete period, I guess. Part B asks us to find the frequency. So the frequency is just going to be the reciprocal of the period. It's 1 over t. So it's 1 over t. Or if you like, you could call it 40 pi divided by 2 pi. But either way, you're going to get, 20. Okay, so 20 oscillations per second. You could kind of think of it like oscillations per second. Okay. And then part C asks us to find E when t equals 0.08. So find the voltage at 0.08 seconds. So we'll say E equals 3.8 cosine 40 pi times 0.08. And you just have to use your calculator for that. Well, maybe not. 8/100ths. Well, 40 times 0.08. Well, yeah, I mean, I'm going to use my calculator. 3.8 cosine 40 pi times 0.08 is about, looks like we've got 3 sig figs, well, 2 sig figs, I guess. So we'll say it's about 3.7 volts, I'm guessing, is the unit of measurement there. That's that. Okay, so that's all I have to say for harmonic motion.